the next installment in reinforcement learning. All right, what we're going to look at in this lecture is reinforcement learning with features. Okay, so it turns out we never want to look in terms of states. There are almost always too many states to reason in terms about, just as we didn't learn Markov, we didn't learn do everything in terms of states. Instead we learned use in terms of features. And in state-based methods, information at one state can't be used by similar states. We want to be able to generalize better. So the idea of using features is we can generalize. And also there are just too many parameters to learn. There are just too many states. And what the idea is we're going to do is we're going to express the value function, which is q, as a function of the features. And most typically we're going to do a linear function of the features or a neural network. So before we do this, we're actually going to use a different game that's sort of bigger, that's big enough to have interesting features, because the previous one we had was only 6 states. So here's the little domain we're going to use. So in this domain there are 5 by 5, there are 25 locations, and the agent can be one of those 25 locations. Okay. So the agent can move up, down, left, right, and these actions are stochastic. And if you go left here, you might crash into the wall. And if you go right here, you might even go left. So I went right there and I end up going down. I can go up there and end up going right. Now, as well as these 25 locations, it's also possible as a prize. So the prize is this blue square. And there's either a prize in one of the 4 outward corners, or there's no prize. So there's 5 states like that. Okay, so there's 5 states like that, and we can go and we can move around. And when we get to the whoops, I tried to go up and went right. I tried to go up. It's quite stochastic. I'm trying to go up there. I went up a little bit. I tried to go up here, and I go right here, and I get and I get a reward. Okay, and I go up here, and now once I stick on that one, I'm trying to get to this other blue one, the left hand corner. Notice there are some white bars there, there and there, and these are walls, so you can't get that way. So we go left here, we go down and then left and then left and then. I didn't go left, I went left, I went left. So it only goes up, and I get to that stage, I get a reward. Okay, so now I can go down again. Alright, so there's 5 times 5 times 5 states, the x, y, and where the prize is. But there's also these funny squares that become red sometimes. So if you notice, there's 5 locations there which become red or not red. And there's where they're monsters. And so what happens is there's monsters, you actually lose points. I think you lose 10 points if you are on a monster when it appears. So if I go up here and then down here and I hit this, I lose minus 10. Okay. Now there's this other pink state in the top left, which is a repair station, which I get undamaged if I go and visit that. So if I keep losing things here, but I go up here, I become yellow. So there's also 2 states of the agent, whether it's damaged or not. So in total, there's 5 times 5 times 5. There's 250 states in this game. Okay. The idea is that the agent doesn't know any of that. There are just 4 actions in each state, and there are 250 states. Right. And so it's actually quite noisy. I think you only get a 0.7 chance of going the direction you want, and there's a 0.1 chance of going in another direction. And notice there we went down accidentally, right. Oh, I got damaged. So now I'm going to do down, and I'm going to get the value, and now I'm going to go left. I go up here, and I either get a choice about whether to become undamaged or go and get the reward. Let's go and get the reward. We go right there, go up, right. Okay, and so now we're still damaged, we got another reward. We're now going to go left, we went up, left, we didn't go left either, left, we went left, oh no, we lost minus 10, we go left, left, and up, and we get undamaged. And now there's a value there. Okay, so that's the game. There are 25 states. There's there's fixed positions where the monsters can be. I think there's 5 positions where the monsters can be. And the idea is to collect these rewards and just go on forever. Okay, this graph shows what happens when we do Q learning on this. So this is we're actually doing Q learning on this with 80% exploration. And if you wander around, and because there's 250 states, you could wander around, and after a while, it's going to tell you what the optimal reward is. Notice in the top left-hand corner here, when the prize is in the top left-hand corner, it's learned to head towards it when it's in that area. Right, in other areas it's not looked so good. In terms of the bottom left area, the best thing to do is to just go down and keep crashing into the wall, it looks like. Okay, so now we're going to, that's after 400 steps. After another 400 steps, we've now done 2,000 steps. Let's make this 400,000 steps. 400, 1, 2, 3, 400,000 steps. Right, now we're going to get there. And now we've got to this stage here. The optimal thing of where we're in this state now is to actually go up and get undamaged. It's learned that. It didn't know anything about being damaged, but it's learned that it's a good idea to do that. If you go down here and you go right here, well, it actually becomes damaged, and it goes right. Whoops, I went right, and then I go right again, and I've worked out the best thing to do is do damaged. So notice it hasn't really learned about becoming damaged yet, because it doesn't really point, when it's damaged, it doesn't point into this pink square. Alright, so let's do another 400,000 steps. Now if you look at the arrows, this is the policy it's going to follow if it's greedy, and it's pretty good about getting to that location. It's not so good about going to the, so now we can follow the policy. You have to go left here, down here, left here, left here, left here. Oh, we end up going down. We have to go up here. Whoops, we go up here. We're up here. Oh, we're going. Notice how we go right here. We go around the monsters here. We've learned about avoiding those monsters. Okay, up. Oh, left. Up. Following the policy, left. Up. Oh, we went down. Still wants to go up though. Up. Up. Oh, we go left. It's actually pretty hard to get there. Up. Up. Oh. Up. Go left. Go up. Oh. Just. Alright. Up. Up. It's just a hint. Whoops, sorry about that. Alright, so here's the same game but with a model-based controller. So this one here is going to learn a model like we did before. Okay, so we're still going to walk around this town. We're still going to let us walk around, but what we're doing now is we're building a model. Okay, so now we're going to do, well, let's actually let it do 10 updates per step. We're going left here. So every time it's doing one action in the world, it's doing 10 steps of model based. So it's still got states, but now it's going to learn this. So if we do 400 of these, we find out it's, it goes there, it actually knows sort of a little bit around this bottom left corner. So the treasure is in this position here in the bottom right. And it's still got, it hasn't learned very much. Do another 400 steps. It hasn't even stumbled on this idea about going up in this left hand side here. Okay, so we had 400, 1, 2, 3, 400,000 steps. We'll find that it's basically learned that when it's in the bottom right here, it should go towards this feature in the bottom right. So it's learned that in 400,000 steps. But that's 10 updates per step. So that's like 4 million updates. Okay, because it's now doing a whole of it's now doing a whole lot of incremental gradient. So it's now doing a whole lot of value iteration steps in between. So it's doing 10 value iteration steps per action. Okay, and we're going to step again another 400,000 steps. Okay, and it's learned, whoops, takes a little bit slower, and it's learned pretty well here. It's actually it's learned to go, at this point here it should go left and down, and it got to there, down, and it's learned to go to the treasure here. When we get to this treasure, it's nothing there, it's actually learned to go down, and it just wants to wait here when it's not damaged. It's sort of down, down. It's pretty noisy. Wants to go up here, and it's going to hang around here until it finds the treasure arrived. And notice how it's going to follow this, trying to follow this path here. It's trying to avoid the monsters that are in these other funny squares. Okay, so we're going to go down, right. Okay, so if we compare these two, this model-based control and the Q-learning controller, look at this one here. The model-based controller had, I just ran it a few times, had a minimum reward of 1,688. That was the minimum reward. The Q-learning had a lower minimum reward, so the model-based controller ended up acting more sensibly, and it had a much earlier zero crossing, back when it's, so some of these are penalties and some of these are rewards, and it actually gets to the point where it crosses the zero. So it's much faster to learn, but it's actually more complicated. Okay, so it actually, so let's go this one more, then it's not about the same number of steps, the same number of actions in the world, but has much more detail. And you notice that the total reward received in the bottom left here for the model-based controller is a lot more than the total-based received for the Q-learning controller. So model-based is a good idea, but uses much more data and is slower, particularly with 10 updates per step. You can imagine doing it with only one update per step, which is this, one update per step, and we'll get to 12 million steps. We'll do this 4 times. 1, 2, 3. Okay. If you do update steps, we still have much more, done about the same number of steps. We have much more reward. The minimum reward was higher, and it crossed zero at much more time before the Q-learning. So this is actually doing essentially the same number of updates as the Q-learning controller, but uses a bit more data structures because it actually remembers the model. So it turns out that the model-based controller is a lot better. Alright, so now we're going to look at what to do with a feature-based controller. Now the feature-based controller is going to generalize better. And so here's the feature-based controller. So this is learns a linear function in here. So what it's going to do here is you can go right here, and we're going to go right here. And because we've crashed into the wall and got a penalty, it knows crashing into the wall is bad. Right, because that was one of the features. So it's learned over all of the states something. So it can actually now, with we crashed into the wall, it received a penalty, and now it's avoided. It thinks crashing into the walls is bad, so it's now going to avoid those things. Okay, so we go up here and up here, and we go left here. We go left here. Oh, now we go up here, left. It's left, up, up. Okay, it's now going to learn that it's only done 17 steps, and it's already got this idea as it wants to go towards the oh, it crashed into the wall. It went there. Now it still knows to go out. Now it's just going to wander around. It sort of knows to avoid the walls because that's a feature that it has. And now it's going to say there's a feature about which way the treasure is, and it's worked out that it's a good idea to go towards the treasure. Okay, and so that's actually the feature. That's all it's learned here. So it's a feature, and it's learned, I got a reward when I did that last time, so I'm going to do it again. Okay, so they're the sort of features we're going to build, and it learns very quickly here. This actually got a minimum reward of just -3 and a zero crossing at step 15. It's not very fair because, right, but and now we're going to get it, so it's going to learn a lot faster, It's already only done, minimum reward was minus 130 at step 415. So it only, and the zero crossing was at 800. Previously crossed, they got to zero reward. So imagine the reward goes down then up, and where it crosses the zero. And here it's at 887, but in the model-based controllers with 31,000. And the Q-learning, it was actually worse than that. So let's work out how this function approximator works. Okay, to do this we're going to review gradient descent. So what gradient descent is to find a local minimum of a real valued function x, f of x. We're going to assign an arbitrary value to x, and we're going to repeat. We're going to take this current point and we're going to update it by the gradient. So each x gets the value of x minus the derivative of df minus x, and it's trying to find the x that minimizes f of x, and it's going to keep following the gradient in the negative way. Eta here is the step size. Okay, so that's how to find a simple one. To find a real valued function of multiple arguments, we're going to assign arbitrary values to x1 to xn, and we're going to repeatedly just go we're just going to go in each direct dimension. For each argument, for each dimension, we're going to go down in that dimension. Alright, so linear regression, the idea is linear regression is you start with a linear function of the variables. We have f of x1 to xn is some weights times each xi, so it's w0 plus w1x1 plus wnx of n. Where these w0 to wn are weights, and it's typical just to decide x0 is just 1, so it keeps the mathematics simple. So now the function we want to optimize is, given a set of examples E, and example E has output xi is ei for each I, and as an observed value the output of E. So let's suppose that. So now we have the error is actually summing over all the examples of the output of E minus the predicted value squared. So we're going to minimize the sum of squared error here. Okay, so f is a function that depends on the input values for each of the example, depends on the weights, and it's just subtracting that from the output of it, and we just minimize the error. So now that's the function. Now error is just the function we want to minimize using gradient descent. So just like we did before, we're going to differentiate it. So each example should update wi. So wi becomes wi minus the derivative of the error with respect to wi. Okay, you should have seen this before. So now we can actually have implemented as gradient descent. We can implement this with gradient descent. So given a set of examples over n features, and each example has input e1 to en, so example E has input e1 to en and output O of E. I'm going to assign the weights arbitrarily, and we're just going to repeat this loop. For each example, the error is the observed value minus the feature value, and for each weight we're going to update the weight gets the weight minus this error term times this probability of ei. Alright, so that's just gradient descent. It's just for each example, we're just going to update each weight by the derivative of the error. Alright, so now let's look at this idea of Salsa. We're going to use Salsa because we want to learn. It turns out that Salsa works better for a function approximator because it's get better estimates of the policy that you're following rather than getting estimates of the, we actually can get good estimates of the policy we're following rather than getting good estimates of the optimal policy. And the idea now is that one-step backups provide the examples that can be used in linear regression. Suppose the f1 to the fn of the features, so the q of w weights depends on w, the bias, w0, plus a weight w1 times the feature value, and this feature value can depend on both the state and the action, plus wn for the feature of the state and the action. Right? And now we're going to, just like in Salsa, we had an experiencer in state S, did action A, received reward R, ended up in state S prime, and did action A prime. That's going to provide an example for us. And it's going to provide an example for Q of S and A. So the old predicted value is Q of S and A. The new predicted value is the reward plus gamma times the future value, just like we've done before. So we always say the old value is the old predicted value, and the new value is the reward plus the discount factor times the future value. And so now what we're going to do is we're going to treat R plus gamma of Q of S prime A prime as a new training example for Q of S and A in linear regression, or whatever other supervised learning we're going to do. So this is a new training example we're going to use for Q and S of A. Okay, so we're going to mix up basically linear regression with Salsa, and we get this algorithm. So here's the basic framework for Salsa. It's given a discount factor gamma and a step size. We're going to assign all the weights arbitrarily, so these are the weights of all the features. We're going to observe the current state. We're going to select action A, and we carry out action A. We're going to observe the reward in the future state, then we're going to select action A prime. So this is exactly the same loop as in Salsa. But now what we're going to do is now, instead of just averaging, we're now going to use the function of linear function approximator. So we're going to let delta be the error, so that's the old, so like before, we're going to use the old value, the reward plus gamma times the future value minus the Q value, but now we're going to use it in gradient descent. So now we're going to do, for each feature, we're going to update each weight by the error times the feature value. Okay, we're going to now have a new state and a new action. We're going to finish our repeat. So that's simply Salsa with linear function approximator. That's what we were doing before. Okay. So in our game, we can define features. So here's the features for that particular game. So we're going to say F1, and these are just sort of arbitrary things I just made up that seemed reasonable. F1 of S and A is 1 if A goes from state into a monster location and to 0 otherwise. This is sort of a monster. Recognizing going into a monster location. This is going into a wall and is 0 otherwise. So if you crash into a wall, you know, it's going to look like that F2 is bad. This is going towards a prize. So F3 is going towards a prize. F4 is the agent is damaged and it takes it towards the repair station. So this one here we've programmed in where the repair station is. This is the agent's damaged and it goes into a monster location. Maybe that's bad. This is just where the agent's damaged, but let's make up another one. This is one at the F7 is just the agent's not damaged. So I just made up this as to see what was going on. The agent's damaged and there's a prize, and there's not damaged and there's a prize in that direction. So we can also have the distance from the left wall if there's a prize at location 0 and at 0 otherwise. So basically this is trying to look at the left wall. So this is trying to say position P's at 0 towards the left wall. And it's also doing the distance from the horizontal position if there's a prize at location F0. And there's all these other ones for different combinations of prize locations and difference for the walls. Okay, so now let's look at what's happening here. Let's reset this game with our reset. Reset this. And now we're going to step down. So we're going to step down. Let's go, say we go down. Nothing happens. We crashed into the wall. You received a reward of -1, but doesn't do anything because you got next got to choose the action we're going to do. We're going to do left here. So now it's learned, if you look at what's happened, we've got a negative thing, but look at the features, what's going on in the features here. So in the features here, all the ones that were true now get a negative value. So F0, so let's move this across to there. So these exactly correspond to these features. So all the ones that were true when we crashed into a wall all get 0. So F0 was true, which is the bias, so that's always drawn. 1 wasn't true, 2 was true, it goes into a wall. So it's learned that if it goes into a wall, it's bad because that was on when it crashed into a wall. 7 is the agent's not damaged, so that also looks bad. 10, all the ones that were true, the distance to the left wall if there's a prize. So there was a prize at them, so F10 was true. Okay, so all these are all the ones that were turned on when it crashed into the wall. But it's learned now to generalize, and so now it's learned, let's not try to crash into the wall. Okay, so that's all that's happened here. We could train it, we could let it go up. Also that it's learned that, you know, it's learned that it's good to go, oh, so it's only done 4 steps, and it's already sort of getting this idea because it actually learns that to F1 is the agent goes to the monster location. It's worth going to a monster location. Alright, so what we're doing here is we've got all these features, we're just updating these features. Let's analyze this. You can play with it on your own. Okay. So there's a whole lot of problems with doing this function approximation. First one is the algorithm tends to overfit to current experiences. And this is called catastrophic forgetting. It's particularly bad for neural networks here because you tend to get lots of experiences all around the same state and you forget about the other one. The solution to this is to remember the old SARS prime experiences and carry out some kind of action replay. So the solution to this is use action replay. And that's very common for neural network type models, which you actually remember previous experiences and you just replay them. Now you could do different function approximators such as decision tree with linear functions at the leaves, which is called a regression tree. And there's all sorts of representations we could do. We could do a linear function of decision trees. We could do a neural network. But they all require some representation of states and actions. You need to actually give it some way to actually represent it. The recent trendy ones in New York have actually been given for neural networks have given it an image. You can actually learn that as our representation, for which we can learn features that are useful. One of the things we could do is we could use a policy to do more than one step look ahead. So instead of now we're basically looking at one step ahead to work out the value of Q of S and A, the optimal policy, what we could do is to look ahead. Look ahead a few steps, so we could look ahead, follow a random path and look ahead that. So later on there's a reading about Monte Carlo tree search, which does multiple lookups in order to get a better estimation of that. So there's lots of variants of function approximation, and maybe for a March project you could play with some and do an experiment and tell us what works or what doesn't work. It's another class of algorithms for reinforcement learning called evolutionary algorithms. The idea here is we're going to maintain a population of controllers. We're going to evaluate each controller by running an environment, and each generation the best controllers are combined to form a new population of controllers. So we're doing evolution so the good controllers reproduce and the bad controllers die off. And so the idea is we're going to try and improve controllers in turn to that. We actually do an analysis of the complexity of that. If there are n states and m actions, there are how many policies? You've got to remember it's n to the m or m to the n. It's the maximum. So for each state, you've got to choose an action. So there are m possible ones for each n state. So there are m to the n policies. Okay. Whoops. Oh, that's interesting. This doesn't work. All right. There are m to the n policies. Whoops. Sorry. And what happens is that the experiences are used weights. So basically there are too many policies. There are a lot more policies than there are. So before we didn't need to look at that many policies. We were actually improving each component separately. And that has a huge advantage in learning things. So all the reinforcement learning algorithms we did not consider policies as a whole, but learned about the components of a policy. It turns out there are just too many of these policies. And it's also used experiences are used wastefully. It's only used to judge the whole controller. And so it also doesn't learn after every step. So the reinforcement learnings learn after every step. And the performance is very sensitive to the representative of the controller, and there are lots of papers in the reinforcement, in the evolutionary algorithms literature that basically say, oh, here's a different way to represent the controllers in here. All right. So we've now looked at different reinforcement learning algorithms, and they're all really based on this idea of we want to improve the algorithm either for each state or for each feature, and learn that every step you can update what you're doing. So these are much better than sort of the reinforcement learning alternatives. Okay, so download those applets from the demos file that's on the link and play with them and see what happens. Alright, let's stop there.